Good day, folks. Welcome to Bright's Mind Academy, where we bring brilliance to every lesson. In today's video, we're gonna look at Theorem 9, and it states that the angle, between a tangent to a circle and a chord drawn from a point of contact, a chord that is drawn from a point of contact, is equal to an angle in the alternate segment. I repeat, the angle between a tangent to a circle and a chord drawn from the point of contact is equal to an angle in the alternate angle. Remember, I said this theorem when I just stated them without showing you. It does not make sense. We were told that, let me do this so that we can see. The angle between a tangent, here is a tangent. The angle between a tangent to a circle and a chord drawn from the point of contact. Drawn from the point of contact. Here is that chord here. Point of contact is here. So here is that chord. Again, this angle between this tangent and the chord drawn from a point of contact. This angle, basically. What about that angle? They are saying now it is equal to an angle in the alternate segment. Alternate segment, it is something like this. Alternate segment, that angle. All right? So basically what they are trying to tell us is that this angle here, B, or rather DBC, it is equal to this angle here. I can call it E. Okay? What this theorem states, it means now this angle here, DBC, it is equal to angle E. Or I can say, all right, this is still my tangent, AC. But now what if I'm talking about this chord here? Because this is also a chord from a point of contact. Again, remember a chord, it is a line that touches our circumference twice. Again, like this here and here. So also this is an angle between a tangent and a chord drawn from a what? From an angle in the alternate segment. Again, what am I saying actually? Sorry. So I'm saying this angle here, ABE, it is an angle between a tangent and a chord drawn from a point of contact here. Again, it is this angle that we're talking about. It is equal to an alternate segment angle. So it means now, if I were to talk about ABE, it means it is equal to this angle here. I believe you are following. I strongly believe you are following. If I have something like this, okay, this is not good. Okay, it's fine. And let me say I have a tangent. Maybe somewhere here. Okay, this is not a perfect tangent. There, like this. It means now, if I'm talking about this angle here, this angle here is going to equal to what? To an alternate segment, which is what? This angle here. This angle here. Also, if I were to talk about this angle here, it is equal to alternate segment, which is which angle? That angle here. Here and here. So this is what a theorem 9 states. Now, this one you are required to prove. This one you are required to prove. Let me try to do this. Okay. Ish. Okay, it's fine. I'll just redraw another one. I'll just redraw another one so that we can be able to prove the theorem. In that case, the of, let me see. I hope you can see here. Remember, an examiner can draw whatever sketch that he or she wants, and no one is gonna tell him or her anything. So if whenever you are used to a certain sketch being like however, then I want to tell you this: you are in danger because no one tells the examiner which sketch to draw. If whenever you are used to understanding whatever sketch, I guess you're duped. Let's name it A, B, C, D, E, center O. Yeah. Now let's prove. We are given a tangent ABC. Tangent ABC. Yes, here is our tangent ABC. Again, you are given center O. I'm not sure how I did not include that. We are given center O. Again, now we are required to prove what? We are required to prove that CBD, angle CBD, 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 this angle here, it is equal to what? That angle there, it is equal to BED, bed. B angle ED. B angle ED. Which angle are we referring to? B angle ED. This angle here. So we are required to prove that this angle here is equal to that angle. Sorry. Now, how can you do that? I normally use this. I prefer using 1, 2, these letters. Saying here it is 1, 2, and maybe 3. This one I did not need to state if it is 1 or not. Even this one I did not need for now. But remember, first thing before construct, you do before you prove, you construct, right? So I'm gonna construct line B going to O like this until the circumference. Then I'm gonna name this M from Paul. Now, one might ask, eventually what happens is that many learners get stuck whether I'm going in this direction or I'm going to that direction. What I can tell you is that you are going to the direction of the angle that you are required to prove. Which angle are we required to prove? This one. So it means you are going to go to that angle. So you're going to construct something more or less like this. All right? Yes. Then let's do this. Now, I want you to see something. This OB, it is a what? It is our radius. Again, OB, it is our radius. Take note of that. And now, MOB in full, MOB in full, it is our what? It is our diameter. Again, yes. Now, if I have named this like this, I think I'm done. All right, I'm going to name these two again. I'm going to say maybe it is E1, E2 here. Yes. Now, how do I prove this? First thing first, I'm going to say, let's see which theorems that we already know that can apply. See this. Do you remember this theorem here? The bow tie theorem. Angles in the same segment. That states that this angle is equal to this angle. This angle is equal to that angle. Sorry. To that angle. Do you remember that theorem we did? Under theorem, I think it's theorem 4. We did this angle. Again, this theorem rather. So, sorry, this All right, let me just remove this and say this is 2. Now, we already seen one theorem that you can use. Another theorem from theorem 3 is this one. If I have a diameter, an angle subtended by that diameter, which is this one, E1 plus E2 or BEM, it is equal to what? 90 degrees. Another theorem that I can use. Another theorem I can use is that if I have a radius and a tangent to a circle, at a point of contact, they make a 90-degree angle. That's the theorems I can see. All right? Sharp. Now, let's use these theorems. Let's first use this one. That says an angle subtended by a diameter is equal to 90 degrees. Meaning angle E1 plus angle E2, it is equal to 90. Let's first use that. Let's use the theorems that include 90. So you're going to say angle E1 plus angle E2. I'm purposely writing it as angle E1, angle E2 instead of angle B angle EM. Instead of B angle EM, I just prefer saying E1 plus E2 so that you can see as I explain what will happen. It is equal to 90 degrees. Why are we saying that? Remember angles, angle in the semicircle. I don't think I gave a reason for 90-degree angle. It is angle in the semi. Or you can also do this. It's fine. Just do semi, semi what? Semicircle. If you do not want to say semicircle, you can say this. You can just do a circle and a dot at the middle. All right. But yes, it is angle in the semicircle. Now, let's check another 90 that we can see. Another 90 that we have, it is this one. OB perpendicular to BC or ABC in this case. But we are focusing on which angle? This one. So I'm going to say B1 plus B2 it is equal to 90 also. We agree. B1 plus B2. Angle B1 plus angle B2. It is equal to what? 90 degrees. Why are we saying that? Radius, it is perpendicular to tangent. You can say radius perpendicular to tan. All right? Now, but now if this angle here, if E1 plus E2 is equal to 90 and B1 plus B2 is equal to 90, this means that angle E1 plus angle E2 it is equal to angle B1 plus angle B2. Why are we saying that? It is because both of them are equal to 90. You don't need to state a reason here. But what? But check now. Despite saying that, look at this. If I do this, I can see that this angle here, angle E2, it is equal to angle B2. That one we know from theorem 4 that states that angle, if an arc or a chord subtends angles at the circumference, those angles are equal. Again, if I have a chord MD and it subtends an angle at B2, subtends an angle at E2, those angles are equal if they are subtended at the circumference. So we can say that E2 is equal to B2. But angle E2 it is equal to angle B2. Why are we saying that? Angle in the same segment. Angles in the same segment. If E2 is equal to B2, then automatically and mathematically B1 is going to be equal to E1. If this is 40 and 40, This is going to be 50 and 50. So therefore, angle E1 it is equal to angle B1. Are we done proving? Let's see. Therefore, angle E1 is equal to angle B1. Let's see. Angle B1 it is equal to angle E1. Let's name them geometrically or yeah, euclidically, if there's that word. We know this angle it is what? DBC. Angle B1 it is DBC. Angle B1. Angle B1 it is D angle BC. Angle E1 it is what? Let's see angle 1. Angle B1. Angle E1 rather it is BED. B angle ED. This angle here. So E1 it is B angle ED. Bed. B angle ED. Now, do you believe or can you see now we have proven what we were required to prove? We are required to prove that BED it is equal to CBD. Let's see. CBD we have CBD. Even if the order that is not correct, but it is CBD. You see, the angle that you are referring to it is this one. CBD. I can say CBD is equal to what? B angle ED. So we have proven that. Please, if you did not understand it, please rewind back. Know all your theorems. This is the first theorem that includes 3 theorems that you should know. The first one is this one. That says tangent is perpendicular to radius. The second one is angle in the semicircle. The third one is that angles in the same segment. This is theorem 8, I think. 7. 8 or 7. I can. Which theorem is this? Oh, so it's gonna be theorem 7. We have theorem 7. We have theorem 3. We also have theorem 4. That you need to know before you can know how to prove this theorem 9. So thank you very much, folks, and I believe you understood what I am trying to explain or what I have explained here today. If you did, please give our video a thumbs up and kindly subscribe to our YouTube channel. Until we meet again, thank you very much, folks.